All right, last class. In chapter 4, we were talking about the mole. The mole is like a dozen, but it's for chemists, and our dozen is much bigger, many, many magnitudes of order bigger. So it's that 6.022 times 10 to the 23rd power. And we can use that to convert, like we did in this step, between molecules and moles. You could also swap out atoms for molecules. You could swap out formula units for molecules. The idea is we're talking about one single thing that goes along with this Avogadro's number, 6.022 times 10 to the 23rd power. We also learned about molar mass. Molar mass is always what we're going to use when we're converting between grams and moles, or moles and grams. It's just that one direction we're dividing, the other direction we're multiplying. Some other things that we can calculate or come up with are things like mass percent composition, frequently just called mass percent. So the mass percent is calculated based off of this formula. So the percent of whatever the element is equal to the mass of that element. So the grams of X divided by the grams of, we'll call it X, Y, Z, so that we can show that there's some other stuff. So how much of it is just X? If we think about our lab yesterday, we did this for oxygen. So if we want the mass percent of oxygen, how much oxygen do we have versus how much is the whole thing? And then we multiply by 100%. Anytime we're doing a percent thing, there's always going to be this times 100%. So as an example, we take a sample of chromium, we react it with oxygen to form 0.523 grams of the metal oxide. The metal oxide meaning it's the chromium and oxygen, not just the oxygen. So this is an often overlooked step. We need to take the 0.523 grams of the metal oxide and subtract from that the mass of the chromium. That will tell us the mass of the oxygen. This is what we did yesterday in lab. So 0.523 grams chromium and oxygen. Subtract out the 0.358 grams of chromium, and that'll give us our, oh, just kidding, we don't need that because we're not calculating mass percent of oxygen. Oh well. So we've got, the percent chromium, we're taking the mass of the chromium. Imagine setting up a problem so that it's convenient to solve. We're going to divide that by the total amount, the 0.523 grams of chromium and oxygen. Multiply that by 100%. You should always get a number that is 100% or less, because it's making up part of the thing. It can't be more than all of the stuff, because it's part of the stuff. 0.358 divided by 0.523 times 100, it is 68.5% chromium. I'd like to take this moment to point out that I went off in the wrong direction on solving this problem. Don't feel bad if you also go off in the wrong direction when you're solving your problems. Any questions about how we did that? Cool. The FDA, the Food and Drug Administration, recommends that a person not consume more than 50 grams of added sugars. That's in a day. If you make 801 grams of brownies from scratch using 422 grams of sugar, what is the mass percent of sugar in the brownies? This is a rough approximation based on the Ghirardelli brownie mix that I have at my house. I thought that this might be an interesting and applicable example, because maybe you also like Ghirardelli brownie mix and you're also trying to track your macros. And so this might be a good example of how you can use the stuff that we're learning in chemistry outside of the class. So we're making 801 grams of brownies. That's going to include 422 grams of sugar. We want the mass percent of sugar in the brownies. So we are going to take the thing that we care about, the 422 grams sugar. The sugar is in the brownies. It's part of the brownies. The brownies also has other stuff in it. So that's going to be the total part. So 422 grams divided by 801 grams. And multiply by 100%. So 422 divided by 801 times 100. Turns out these brownies are roughly, again, I didn't make the brownies, this is just a guess, they're roughly 52.6% sugar. So if my math is like in the right neighborhood, half of what you're eating when you're eating those yummy, tasty, delicious brownies is just sugar. That might be off-putting, that might be appealing. It might just be like, whatever. The Food and Drug Administration doesn't own me, I do what I want. I'm a strong, independent woman, or man, or other. So we calculate the mass percent composition of the sugar in the brownies. I rounded mine a little bit differently in this example up above for 3 significant figures. Let's say that we rounded it off for 4 significant figures, we had a better scale or something. Another thing that we can do is we can use that 52.69%. We can use this as a conversion factor to calculate the amount of brownie that we can eat. So this 52.69%, let's look at our formulae. Grams of sugar, grams of brownie, times 100%. This is one of my least favorite sets of slides because I always forget how to explain mass percent composition as a conversion factor, which is just so fun to do on the fly. To make this convenient, because it's a percentage, with percentages oftentimes we can make things convenient for ourselves. I believe what we want to do here is pretend like we've got 100 grams of brownies. If we've got 100 grams of brownies and we've got 100% here, magic happens. Wow, magic. So our hundreds cancel out. Nope, that's not it. Dinkelberg. All right, well, I'll just give you what it is. You can make it 52.69%, whatever the percentage is, but grams sugar over 100 grams brownies. That's what I was trying to get to. That's our conversion factor. I just don't remember the math of how to get there. You can also make this percentage into a decimal form, which is basically what you've got here. If you do the math, if you do the 52.69 divided by 100, this is the same as 0.5269 grams sugar per 1 gram of brownie. Those are exactly the same. I just don't remember the algebra to make the formulae do that for us. All right, so let's look at how we might use this to our advantage. What mass of brownie can you eat without exceeding the 50 grams? suggested daily value for added sugar. Our brownies, again, 52.69% sugar by mass. So that 52.69% sugar by mass is important. This 50 grams is important. Those are both givens. And we want the mass of brownie. How much brownie can we eat and stay below that 50 grams of added sugar? This is, of course, assuming that we eat no other added sugar in the day, which is unlikely. So starting with 50 grams, I'm starting with 50 grams because 52.69 is our conversion factor. I like to start with the thing that's got the simplest units. The 50 grams is going to be the simplest units. This 52.69% means that we've got 0.5269 grams sugar in every 1 gram of brownie. That was that we magically arrived at this as a conversion factor now, and I skipped all the algebra, which I can definitely do, believe me. This 50 grams is 50 grams of what? Brownie or sugar? Sugar. It's important that we know that it's sugar because we've got grams of sugar, grams of brownies. We want to make sure that we're using this correctly. So if we've got grams of sugar and grams of sugar is on top in our conversion factor, do we want to apply it as it's written or do we want to invert it so that it's 1 gram brownie over 0.5269 grams sugar? Which one do we want here? The left one in green or the right one in blue? We want the right one so that the grams of sugar cancel out. So we're dividing by our percent composition. So cancel those out. We'll get grams of brownies left over. We do 50 divided by 0.5269. Turns out we could eat up to 94.89 grams of brownie. And I don't know if the FDA intended for 50 to be one significant figure or two significant figures, or if they don't really care. But the way that I would look at this on a scale, I would say, all right, if I'm trying to hit my 50 grams of sugar and no more, I'm going to weigh out about 95 grams of brownie. If I'm a little bit over, it's not the end of the world. It's not going to kill me, at least not today. So about 95 grams of brownie that we can eat. So about 3.3 ounces of brownie, or 1/5 of a pound, roughly, which I don't think is very much brownie, unfortunately. Questions about eating brownies? Now we're all going to go home and make brownies. Another thing that we can do with percent composition, we can calculate it from a chemical formula. You don't need to know the amounts of anything that you have. We can just, based on the formula, calculate the percent composition. This is easiest to do if we assume that we've got 1 mole of the chemical. You can assume that you've got any amount, but trust me, 1 mole is the easiest. So we're going to pretend like we've got 1 mole of this C8H18 octane. That's what's one of the big components of gasoline. So this C8H18, we want to figure out what the molar mass is for it. So for carbon, we've got 8 of those. They're 12.011 grams per mole each. For hydrogen, we've got 18 of those, 1.008 grams per mole for each of those. I am going to actually calculate these out individually. So for carbon, it's 96.088 grams per mole. For the hydrogen, 18.144 grams per mole. In total, 114.232 grams per mole for C8H18 octane. So we want the mass percent composition of hydrogen. So we want the grams of hydrogen over the grams of the whole thing, that's the octane, times 100%. How do we figure out how many grams of hydrogen we have? We've got grams per mole. So this is where pretending comes into play. We pretend we've got 1 mole of the chemical. If you multiply 96.088 grams per mole, or 18.114 grams per mole, or 114 grams per mole by 1, it's the same number. So our grams per moles turns into grams. And the two that we care about are for hydrogen and octane, C8H18. So multiply these both by 1 mole. And we have got 18.144 grams of hydrogen and 114.232 grams of octane. So that's why 1 mole is the easiest. Again, you can use any amount that you want, but 1 mole means that you don't have to use your calculator quite as much. Any questions so far where we got those? So again, we want to pretend we have 1 mole, just because it's the easiest. Now we can plug these in to our formula. Our 18 grams of hydrogen, our 114 grams of octane times 100%. And it's about 15.88%. We would maybe go an extra decimal place, but the sig figs aren't really that important here. Yeah, that's where I wanted to put that. All right, one for you to try. Acetic acid is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. I'll give you a couple minutes to try this one. All right. To start with our mass percent composition, we want the mass percent composition of oxygen in acetic acid. We are given the formula, the molecular formula of acetic acid, HC2H3O2. We need to figure out what the molar mass is. So find molar mass of HC2H3O2 and oxygen in that, in vinegar. So specifically the amount of oxygens that we have in this chemical formula. So our components are carbon, hydrogen, oxygen. We've got 2 carbons, total of 4 hydrogens and 2 oxygens. It's a common mistake that I see when students are calculating molar masses or counting up the number of hydrogens for things like this, where we've got one H in front and then a couple more behind it. Sometimes they forget to add those numbers up. So they might put 3 or they might put only 1 for our hydrogens. We've got 1 plus 3, we've got a total of 4 hydrogens. And then we multiply these by our molar masses. I'm going to sum them all up. And I'm also going to pull out this 2 times 15.999 grams per mole separately. So 2 times 12.011 plus 4 times 1.008 plus 2 times 15.999. The total is 60.052 grams per mole. That's our molar mass for acetic acid. For just the oxygens by themselves, it's 2 times 15.999. So that's 31.998 grams per mole. For mass percent composition, we need masses, and we currently have molar masses. What is our fun trick that we can do here? What can we do to make our lives easier? Multiply by 1. Yeah, multiply by 1 to get rid of our units of moles. So assuming that we've got 1 mole, moles cancel moles. We've got 60.052 grams of acetic acid and 31.998 grams of oxygen. So take the 31.998 grams oxygen, divide it by the 60.052 grams of HC2H3O2 times 100%. So we filled out our mass percent composition formula. And put it in the calculator. We get 53 point, let's call it 284%, something like that. Questions? All right. We can also calculate a chemical formula from mass percent composition. This would be the empirical formula or the experimental formula, or another way of thinking of it is the simplified formula, so smallest subscripts. We've already got a little bit of practice with this thanks to our lab yesterday. So as a reminder, our empirical formula gives the smallest whole number ratio. It's got the simplest subscripts. So like if we had C8H18, we can divide both of these by 2. We would get C4H9. Those are now both no longer divisible by the same number except for 1. So that would be an empirical formula. The molecular formula is a whole number multiple of the empirical formula. Another example would be ethane, C2H6. This is the molecular formula for ethane. We could turn it into the empirical formula. turn it into the empirical formula by dividing both of those subscripts by 2. So we'd have CH3. And that whole number multiple, in this case, was 2. So if we take the subscripts of the empirical formula, the CH3, multiply it by 2, we get C2H6. It's working the other direction. If we're working with experimental data like we were yesterday, let's say that we did this fun chemistry experiment that you shouldn't do at home, but you could do at home, but you shouldn't do at home. It might be fun, but also you shouldn't do it at home because it's dangerous, because you might kill yourself. So don't do it, because you shouldn't. If we were to do this fun science experiment at home, we take a sample of water and we decompose it with electricity. This, let's say, produces 4.5 grams of hydrogen, 36 grams of oxygen. So that's the masses of each of our components. How would we go about determining an empirical formula from this data? Well, we've got steps. There are steps to solve this type of problem. The first thing that we would want to do is start with the masses of each element. So the amounts that we were given, and I underlined those in the previous slide. We will see those again in the next slide. If we are given percentages, assume you have 100 grams, and that will turn the percentages into grams. Or if you don't want to remember the math reason why that we can do that, you can just remember that we can do it. And anytime you see a percent, just turn it into grams for specifically experimental data like this. Then we want to convert mass to moles using molar mass. Our formulas tell us the relative number of atoms of each thing. The atoms are different sizes. Some atoms are really big, really massive, really heavy. Others are really small. And so if we're doing it by grams, that's just telling us like what the scale would read out if we just put those atoms on the scale versus if we put the other atoms on the scale. So it's kind of an apples to oranges comparison, because some of them are heavier, so we might only have 1, but it weighs the same as like 5 of this other thing. If we divide by the molar mass, that's like counting all of the individual atoms. So then we can compare the countable number of atoms to the other countable number of atoms. Then to get a ratio, we divide all the moles by the smallest number of moles. Technically, you can do it by any of the numbers of moles. It's easiest, probably for most of us, all of us, if we divide by the smallest number of moles. So this will give us ratios of the elements relative to the one that we've got the smallest. So our smallest number for these ratios will be 1, and then we'll have other numbers that are bigger than that. If the mole ratios, rather, are not whole numbers, we can multiply all these mole ratios to try to get close to whole numbers. And this is the part that really screws with people's minds. This really, I feel like people's brains melt when we get to this step. Not everyone, but a lot of people. So this is a table in the bottom right of the screen, right? We've got fractional subscripts. So if your number ends in any of these or something really close to them, pick the closest one, then you can multiply by one of these numbers after it to get all of your numbers to whole numbers. There are other options beyond what's listed here. Typically on exams, you're going to end up with something that's got basically right on one of these nice, neat fractional subscripts. So you can either memorize this table, or another thing that you could do is just make guesses about what you need to multiply by. So you could just take whatever your mole ratio is, times 2. Okay, that didn't work. Divide by 2 times 3. That didn't work. Divide by 3 times 4. You can just work through a bunch of different numbers until you get something that's close to a whole number. That would be one way to do it. Or if you know what these fractional subscripts turn into, congratulations, you've already got this table in your brain. And then we're going to write out the formula using those numbers of moles as subscripts. Sometimes, especially if we're working with experimental data, we'll give ourselves a little bit more leeway, a little bit more leniency to just round up to the nearest whole number or round down to the nearest whole number. So like a lot of us ended up with our ratio for oxygen yesterday of like 1.07, 1.08. For experimental data, we know that there's a little bit of plus or minus. We probably didn't do things perfectly, so I just said go ahead and round that down to 1. On exams, in like made-up problems, you're going to end up with something that's a lot closer to one of these fractional subscripts, or you'll just have whole numbers. So if you get confused with this, you're not alone. The problems in exams will work out nicely. If you get something that's like 0.33 or 0.66 or 0.50, that is not close enough to round. You need to multiply by something. So we do a decomposition of water. Let's follow through those steps. We want the masses of each of our individual elements. So 4.5 grams hydrogen, 36 grams of oxygen. That's our first step. Just get everything listed out. I like to do these in parallel. So I'll do this hydrogen line. Everything after that will all be the hydrogen. For the oxygen, everything after that will be just the oxygen. So we're running kind of the same sequence of steps all at the same time. Grams tells us the mass, but we know that our atoms are different sizes. And so we want to get to something that we could count. So we're going to divide by our molar masses. If you don't like those line things, we could also do it like this, 1.008 grams per mole. So this will convert us to moles. For oxygen, 15.999 grams per mole. This also gets us to moles. So we do a little bit of math. We get 4.464, and our fun little trick of not writing everything out, ... As a reminder, or in case I haven't talked about it yet, this ... means there's other numbers there. And we didn't forget about them. We didn't forget about them, sort of meaning we are continuing to use them. We're using all the numbers. We're not rounding. Mr. K, we're not rounding. I promise, I'm not rounding. But also, I don't want to write them out. So that's a shortcut that you can use. Make sure that you don't round, though, right? Because that's part of how we're able to use that. So that's 4.464 and some change. Moles, hydrogen. For the oxygen, it ends up being 2.25 ... moles oxygen. If we're doing this ... and we're keeping track of significant figures, make sure that you have enough numbers written out so that you can keep track of your significant figures. So you wouldn't do 2. ... because then we wouldn't have enough significant figures. That's an aside. All right, so we've got these numbers of moles. Wow, these look ugly. Those are not nice numbers if we wanted to try to multiply them by something. Fortunately, there's another step. What's the other step? We've got our numbers of moles. What we're looking for, though, is how many of one do we have for the other? How many hydrogens do we have for every oxygen? How many oxygens do we have for every hydrogen? Kind of something like that. We divide all of them by the smallest one. For things where it's just two things, that's nice and easy. So this 2.25, that's our smallest number. So we're going to divide both of these. Divide both of these by our smallest number. and this will give us our ratio on the top. This is our ratio of hydrogens to oxygens. On the bottom, this is our ratio of oxygens to oxygens. We learned something profound here. The thing that we learned that's profound, we get to do this bottom one for free, is that for every one oxygen, we have one oxygen. Incredible. And for the top one, we get 1.984 ... hydrogens for every oxygen. So for every oxygen that we have, we've got 1.984 hydrogens. Don't freak out. Is this close enough that we can round it? Is that 1.98 close enough that we can round it up to 2? Yes. Yes, we should round that up to 2. If you wanted to try multiplying that by something to get it to a whole number, it would be a very large number that you'd be multiplying it by, and then our chemical formula would start to look pretty ridiculous, because it would be like 501 or 208 to 1, or to 200 or something like that. It'd be something ridiculous. So for things to be reasonable, we're going to round that to 2. So we've got 2 hydrogens for every oxygen, 1 oxygen for every oxygen. So the 2 becomes a subscript for hydrogen, the 1 becomes a subscript for oxygens. So H2O. Questions about the process? What might work as a rule of thumb, might work, doesn't always work probably, but might work, is if it's 0.1, if you're rounding more than 0.1, you probably shouldn't be rounding. If it's like a supplied problem. If it's experimental data, there's a little bit more leeway, maybe come and ask me. But if it's a problem that's given to you like on an exam or on a homework, if you have to round more than 0.1, you probably shouldn't have rounded. So if this was like, as an example, if we had like 2.20, that might be 2.20. We could maybe also make it 2.25. So this left one we would multiply by 5. This right one we'd multiply by 4. But we would not round that down to 2, because that would be too far. That might be a nice, if you need a rule for how far we can round, then maybe plus or minus 0.1 for rounding might work. All right, I'm going to give you one to try after this first one. So we'll do another example. A sample of a compound is decomposed, broken up in a lab, and produces 34.97 grams of Fe, 15.3 grams of O. We want to calculate an empirical formula. So we've got our grams of iron, got our grams of oxygen. Start writing our lines of math, our calculation lines. So starting with our grams of each element. They're different size atoms, they're different size elements. We want to get them to something that we can count. We're going to divide by our molar masses. So I'm pulling out my periodic table because my eyesight's getting worse, or I woke up poorly today. One or both, or all of the above. Fe 55.85 grams per mole. Oxygen right around 16. the grams cancel, these turn into moles, Fe, moles, O. So 0.626 dot dot dot. 0.939 dot dot dot. So that's the actual number of moles that we have. We want to know the relative number of moles because, frankly, these numbers aren't very nice to look at. We're going to divide by the smaller one. Divide by the smaller one so that our smallest number is 1. Everything else is bigger than that. Fractions kind of freak people out a little bit. Sometimes we'll end up with things we don't have to multiply anything. If we divide by the bigger one, then we'll end up with something. We'll always have to multiply by something. So it possibly saves us some work. So we're going to divide by the amount of iron. I should have done that in a different color. Divide by the amount of iron. So this top one's free because it's something divided by itself. So 1 iron for every iron. And for problems like this, we're using a number that we just calculated. If you've got the TI-36, might also work for some of the other TIs. If you press up and select the item, you press enter, it'll pull that number out for you, so you don't have to type the whole thing back in again. So I go up and select that 0.939, press divide, go back up and select that 0.06, press enter, and it's way faster than typing the numbers in. So we've got 1 Fe and 1.500 dot 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 O. Can we round that 1.5? Yes, but not to 1 or 2. It's really stinking close to 1.5. So we're just going to call it 1.5. That 0.5, though, is a problem. We need to get rid of it. How do we get rid of 0.5? What can we multiply 0.5 by to make it a whole number? 2. So we're going to multiply both of these by 2. That ends up with 2 for Fe and 3 for O. So our formula, our empirical formula, is Fe2O3. Taking these numbers, these 2's and 3's, and making them the subscripts in our formula. We put the iron first because it's a metal. Questions? All right, one for you to try. Sulfuryl fluoride is a fumigant, a gaseous pesticide that's used to treat termite infestations in houses and has the following mass percent composition. Calculate the empirical formula of sulfuryl fluoride. So the flavor text at the front. If you see houses that are like tarped up to look like they belong in the circus, it's not because they're training clowns, it's because they're fumigating the house probably for termites with sulfuryl fluoride and a little bit of chloropicrin. All right, that was a little bit of time. The chloropicrin, in case anyone was wondering, is just so that if people or animals go into the house that's getting fumigated, sulfuryl fluoride is odorless and it doesn't cause you to react, so you wouldn't know that you're getting slowly poisoned. So the chloropicrin is there. It'll make your eyes water and make you feel bad things to let you know that you're not supposed to be there. That's all. Just in case anyone was wondering. So to start this problem, we ignore all the flavor text, as fun and tasty as it is, and we skip straight to the percentages. We would want to remember we can convert percentages into grams. The assumption that we're making is we have 100 grams of whatever the thing is, or we can just convert it to grams and not think about that at all. That's fine too. So 31.42 grams S, 31.35 grams O, 37.23 grams F. Divide these by their molar masses, and we'll get, this one's, what color did I use? Blue. Divide by 32.06 grams per mole, about 16 for oxygen, and 18.998 for fluorine. We get 0.98 ... moles of S, sulfur 1.95 ... moles of oxygen, and 1.95 ... moles of fluorine. The smallest of these is the sulfur, so we're going to divide all of these by 0.98 moles of sulfur. So we're setting our baseline. Sulfur is the smallest. How much of everything else do we have relative to our sulfur? The top one we get for free. We've got 1 sulfur. The other 2 we get to put into our calculators. For oxygen, we get 1.9994 and some other stuff. Oxygens. And for fluorine, we get 1.9995 and some other stuff. Fluorines. Are those close enough that we can round them, or should we multiply by something? Yeah, those are definitely close enough we can round them. So we're going to call those 2 and 2. So then our formula would look something like SO2F2. If we saw this on an exam, it's entirely possible the order of the chemicals would be different. So it might be SF2O2 or F2O2S. We would just pick the one that's got all the same elements and numbers, just possibly a different order. Questions about that one? All right. Percent of water in a hydrate. We will be using this in one of our labs, one of our future labs. Wow, we're learning stuff before we use it. Isn't that cool? Many ionic compounds. What's an ionic compound? How can we tell something's an ionic compound? Pop quiz. Metal. And a nonmetal. Alternatively, cation and anion, since we can have NH4+. But what I was looking for was, there's a metal. So many ionic compounds naturally contain water molecules. Or if they don't contain water molecules, they will pull the water molecules out of the air. So any oxygen or any water that's in the air, which is usually a little bit, those ionic compounds will greedily gobble it up, pull it out of the air. If you drink a lot of water, you'd be well hydrated. Hydrated, having water. You're full of it, full of water, because you're well hydrated. Ionic compounds, if they contain water molecules, are often called hydrates. because they have water. So it's the same for you as it is for ionic compounds. If you drink water, if you've got water in you, you're hydrated. If the ionic compounds have water in them, they are also hydrated. So a hydrate is an ionic compound. A hydrate is an ionic compound that has water in it. You can remove the water a lot of the time by heating it, which is what we'll be doing in the lab. So if you heat an ionic compounds have really high melting points, really high boiling points, but the water is usually not stuck on there super well. So if you heat it to like a couple hundred degrees Celsius, so like baking it in an oven or hotter, you can often get those water molecules to leave, and what you're left with is just the ionic compound, and we call that anhydrous. So the an prefix there meaning without, and the hydrous part meaning water. So if it's hydrated, it's got water. If it's anhydrous, it doesn't have water. Anhydrates often have fun colors, so this cobalt 2 chloride hexahydrate has this really fun kind of magenta color. Epsom salts are a hydrate of magnesium sulfate, and the formula looks like this. So MgSO4, and then it's got the dot. The dot is not multiplication, even though we'll often use a dot for multiplication. The dot means associated with, or just with. So for every MgSO4, there are also 7 water molecules attached. How they're arranged, somebody knows, I don't. But they're in there. So for every MgSO4, we've got 7 water molecules that are also in there somehow, somewhere. And the full name for this would be magnesium sulfate. Mg is magnesium. It always has the same charge, so we don't have to include the Roman numeral parentheses. Sulfate, SO42 minus, sulfate. And then we name the hydrate part. So the hepta is our prefix for 7. And here in orange, go Tigers, hydrate is what we call waters. So what would be the full chemical name for gypsum, which has this formula? What's the Ca? Ca is calcium. Calcium always has the same charge or can have different charges. Which is it? What charge does calcium form when it's an ion? 2+. The fact that we knew that it was 2+ and we didn't have to guess always has the same charge, so we don't have to specify. So calcium. And we saw SO4 just up above. Right, so it's still going to be sulfate. And we've got 2 waters for every one of our calcium sulfates. So we have to name this. The H2O part is hydrate. And we've got 2 of them. Our prefix for 2 is di. So calcium sulfate dihydrate would be the full chemical name for gypsum. Questions about naming? All right, we can also find percent water in a hydrate. This is similar to mass percent in that it's the same as mass percent, because it is mass percent, but it's just specifically for water. So we're looking for the grams of H2O over the grams of the whole thing times 100%. So we need to get a molar mass for the whole thing. We also need to figure out how much do all of our waters weigh. What's their molar mass? So let's break it down into all of its individual elements. We've got cobalt, we've got chlorine, we've got hydrogen, we've got oxygen. How many cobalts do we have? One cobalt, and it has a molar mass of 58.93 grams per mole. How many chlorines do we have? Two. Two because of the subscript of 2. And those have a molar mass of 35.45. How many hydrogens do we have? 12. So 6 times 2, we've got 12 hydrogens. So 12 times 1.008 grams per mole. How many oxygens do we have? 6. So 6 oxygens. 6 times about 16. Add this all up. And also we're going to get just the water part. So 58.93 plus 2 times 35.45 plus 12 times 1.008 plus 6 times 15.999. The whopping grand total for the whole thing, 237.92 grams per mole. For just the waters, it's 108.09 grams per mole. And what was our fun little secret trick that we could do to get these to grams? Multiply by 1 mole. Pretend like we've got 1 mole to make our lives easy. So times 1 mole. So the moles cancel. Right, and then these are our, I drew those arrows to the wrong spot. These are the amounts that we put in to our percentage. So now that I've used up most of the space drawing in those arrows, let's do the rest of the calculation. So 108.09 divided by 237.92 times 100. This would be 45.43% water by mass. Again, the sig figs are a little squishy here. I don't particularly care if they're exactly right. We can use 4. We could probably even use 5. Questions? Other fun stuff. Oh, did I make this multiple slides? Cool. We already did the molar mass of cobalt-2 chloride hexahydrate, so we'll skip that. Another thing that we can do with empirical formulas is determine molecular formulas. So the molecular formula, we've talked about this before, is always a whole number multiple meaning you multiply the empirical formula subscripts by 1, 2, 3, 4, etc. and you'll get your molecular formula. We can figure out what that whole number multiple is. We call it N, just N for number, by taking the molar mass, that's the molecular molar mass, or molecular formula molar mass, and divide it by the empirical formula molar mass. Then we can multiply all of the subscripts by whatever that number is to get our molecular formula. For example, the empirical formula of fructose is CH2O. So our empirical formula is CH2O. Its molar mass here being its molecular molar mass, is 180.2 grams per mole. What's the molecular formula? So we want to do molar mass over empirical formula molar mass. This will give us whatever our N value is. So we need to calculate our empirical formula molar mass because we don't have that yet. We've got a carbon, we've got 2 hydrogens, we've got an oxygen. So real quick running through some calculations. And our empirical formula molar mass is 30.026 grams per mole. So 180. I'm so good at writing, I do it in the wrong order all the time. 180 divided by 30.026 grams per mole. This will give us a number that's right around 6. You'll always get a whole number. You should always get a whole number, rather. Sometimes you might not get a whole number. If you don't get a whole number, something's wrong. So you should always get a whole number. So we're going to take this 6 and our empirical formula. So CH2O multiply all of those by 6. So we get C6H12O6. Questions? Would we like to do /C another one? All right. Here's another one. Estradiol is an estrogen steroid containing carbon, hydrogen, and oxygen. Its empirical formula is C9H12O. Its molar mass is 272.4 grams per mole. Find its molecular formula. All right, a little bit of time has passed. We've got an empirical formula and a molar mass. We need the empirical formula molar mass. We've got 9 carbons. We've got 12 hydrogens. And we've got 1 oxygen. We'll do the multiplication, add them all up. It's about 136.194 grams per mole. Then we're going to take our molar mass, divide it by our empirical formula molar mass to get N, the thing that we divide by. So 272.4 grams per mole divided by 136 grams per mole. N is right around 2. Then we take our empirical formula, our C9H12 H12, there we go. And we multiply our subscripts by 2 to turn this into C18 H24 O2 for our molecular formula. Questions? Great, then we'll stop there. That is chapter 4.